uh, blog. So welcome, Vikash. So Vikash is currently a research scientist at FAIR. Before this, he was at UW doing his PhD. He made contributions to Mujoko, did a lot of exciting work with dexterous manipulation. There was this Android hand suite, the SHAP hand suite, and a lot of other things which came out of Vikash's work. Then he spent time at Google Brain, and I think he was working on some low cost like suites that he released. And now today is going to talk about rethinking dexterous manipulation, which is a topic which many of us are excited about. So Vikash, thanks a lot for coming again, and please take it away.
All right, thanks, Pulkit, for having me, and thanks everyone for joining. So let me start by just kind of drawing your attention to these pictures on the left. What if I told you that all these pictures are pictures of a human hand? And this is kind of intriguing, is how amazing they are, how expressive they are, how dexterous they are. And this got me intrigued in the incredible dexterity that humans have. And so I've been training as a roboticist to impart these dexterity to robot hands. And today I'm going to share what I've learned so far, maybe some insights into a few of the algorithms, and maybe towards the end, some experiences over a long course of time pursuing this dream. Okay, so let's start. So during this time of sheltering in place, I think we can all relate to this orangutan, which is doing her best with what she has, which is just one piece of cloth. And using that, she's trying to build a hammock. There are two important things I want to call out here. First, she's using her intuitions and foresight, which we commonly term as models, to test the strength of these knots. And she's not happy with those knots, so she tries again to retie another one. And the second thing is notice her dexterity as she ties those knots based on the intuitions or the model she has so far. And using these two ingredients, she builds herself a functional hammock. The behaviors and the strategies displayed here were truly remarkable. Now, think of the favorite robots that we have so far. And this is the kind of behaviors that we usually see. Or let's say if we give the same piece of cloth to any of those favorite robots we might have in someone's lab and ask it to build a hammock, I'm not quite sure that the same outcome will be the same. So the behaviors that we're able to achieve today is roughly equivalent to that of early primates that have foraged for food and other essentials. And we are seeing increasingly capable of robots foraging objects in increasingly complex situations. Although subtle, but there are two common themes in all these results. One, they use simple parallel geographers. And mostly, these results are limited to pick and place results. One might wonder why this is the case, and I will say this because that contact-rich manipulation of free objects is an extremely difficult problem, arguably one of the most difficult of the robotics ones. And most of these results are primarily vision-based results, which are just disguised with some robot movements on the top. So these are not purely dexterous or impressive in terms of the motion primitives they display. So arguably, the most important milestone that sets most primates apart from other animals was when we started aggressively manipulating the environments to our favor. And this is going to be the next critical development phase for robotics as well. And to succeed in this phase of dexterity in human-centric environments will be the key challenge to master. However, the trajectory that we are currently at is at best going to lead us to this really, really smart crab with parallel geographers that knows how to pick up a screwdriver, but doesn't know how to use it, or doesn't even have the dexterity to use it. And we definitely don't want to be like this crab. So how can we be like this orangutan, which has incredible dexterity to manipulate the environment to our own favor? So the claim so far is dexterous manipulation is hard. So let's try to understand why this is hard. I'm not claiming I know it all, but one way to understand the complexity of any task that you're trying to do is to look at this interesting metric, which is called the number of contact transitions that are involved in this task. Home appliances solve easy tasks because they seldom make any contact, and they're on the left side of the spectrum. And you might Note that they are widely ubiquitous in different ways for different tasks. As we move towards the right, the number of contact transition increases. The problem gets increasingly hard, and the technologies get increasingly rare. And we have mostly achieved solutions on this right side of the spectrum by significantly constraining the system and finding solution space that are very narrow. For example, in industrial pipelines, we create very structured environments, and the outcomes or the behaviors that you're looking for are very specific. The dexterous manipulation is on far right of the spectrum. And what we are trying to achieve is to solve for free-form behaviors where there is no structure in the environment. So this is an incredibly hard problem. It involves searching for effective forces and torques to apply at individual joints such that not the joints, but the objects have to do something else. So it's not about yourself, it's about what effect you bring in the environment. It involves searching for appropriate behaviors to bring interesting effects on the environment. As some of the environment objects move around the workspace, there is an abundance of intermittent contact, all fighting to stabilize the object now. And these contacts are highly nonlinear events that introduce very serious discontinuities in the search space. And this search space is also full of constraints, both coming from the robots as well as joints and the action limits, and as well as task constraints, such as maybe turn the screwdriver, but do not drop it. And finally, the resulting space is highly nonlinear due to the existence of dynamic phenomena, which can be deformation, rolling, slip, which makes finding solutions in this space for stable solution really, really hard. Well, we definitely have made a lot of progress so far. Traditional methods explicitly reasoned about various limits and contact events. While it's possible to define those things for simple grippers and simple tasks, they've started failing when we started to scale them towards more dexterous freeform manipulation tasks. So then there is a wide variety of trajectory optimization-based approaches that don't need this explicit reasoning, but the spatio-temporal synchronization of the hand and the object needs heavy reward engineering for stabilized optimization in this case. The fingers make delicate movements, which are in sharp contrast with the movements that the arm make, which are wide and long. Additionally, they also need very perfect sensing. As you can see on the right, this Atlas robot is roughly doing the right thing, but small mistakes in sensing make it collide, and then the whole system collapses. Now, recently, learning-based paradigms are emerging as great mechanisms for acquiring complex behaviors, and they learn by directly interacting with the environment, which relaxes some of the engineering and sensing demands we have posed so far. However, they learn using trial and error-based optimization, and it is very inefficient, especially in high-dimensional problems. And another problem is the behaviors that they can come up with is totally unsafe, or mostly unsafe. The one on the far right, you cannot imagine a humanoid even attempting to run around that with like legs kicking its own butt. While these techniques, I will say, are rapidly improving, in their current form, they are too inefficient or unsafe for the real world, especially for the robotic hand technology, which are soft and fragile system costing over $200,000. So this hand video on the right is a representative example of the behaviors that I see in my hardware experiments. And the number of times I've broken my own hardware is an embarrassingly large triple-digit number that is nowhere to be proud of. So one common approach to sidestep most of these issues is to undertake the challenge in simulation. And the sim to real has been a very successful paradigm in this. And then we deploy these systems in the real world after the sim to real transfer. But some of the aspirations that we have as roboticists and machine learning folks is to develop robot and agents that can help in some complex situations, such as aging populations stay financially independent, or robots helping underprivileged with better health and sanitation services. And such simulation-based techniques will not be effective here, as these real-world problems are in unstructured settings. And it can be really, really difficult to express in simulation with reasonable details. So in order to realize the promise presented by these emerging data-driven approaches, especially for context-rich tasks, we need further developments. And I'm going to argue there are three today. Potentially there are more. First, we need efficient and practical techniques that can acquire complex behaviors. Second, we need these techniques to be real-world ready. And third, we need scalable and robust infrastructure that can take these developments into the real world directly. So for the first part of my talk, I'll focus on practical techniques and present some algorithmic paradigms that we have found to be very efficient in developing context-rich complex manipulation. But quickly, any thoughts, any objections so far? All right, let's move on. So most of my discussion on the algorithmic paradigm is going to be focused around model-based methods, which have seen very great progress in the past decades, and there are abundance of great results. I'm going to start with one representative example of robot catching objects from odds group at EPFL. A general backbone behind such algorithms look like something like this, that we gather a rich, let me find my pointer real quick. Okay, all right, cool. So the backbone roughly looks like this. We gather a rich data set from the real world, and then we use this data set to model M hat, which is the model of the world. And then we use this model to optimize for the policy. And once we have a policy, what we do is we execute this policy in the real world. And we achieve behaviors like this. So now this plan works great as long as there are few things that is in place. One is the tasks and environments are known ahead of time, and we have the time to gather appropriate data sets ahead of time. And second, that the learned dynamics model, M hat, appropriately captures the real world dynamics everywhere that this policy pi might take you. Well, this is great, but in this talk, what I'm going to do is I'm going to focus on developing model-based methods for unknown real-world settings where none of these hold true. We don't really get a prior information about what the world is or what the task is going to be. And we have to gather data set and understand the underlying structure on the fly as you're trying to solve the task, which was the case for this orangutan over here. And furthermore, both dynamics as well as the policy objectives are non-stationary. For example, think of the orangutan trying this knot. It doesn't know if the knot is stable or not yet, and then it has to change its policy into testing this knot, and it's updating its model that yes, it's strong, not strong, okay? Once it realizes, no, something is not going well, now there's a change in policy. So there's a constant non-stationarity happening between model and the policy that is happening in these settings. So what I'm going to argue that most of the model-based techniques that is coming out today is what we call as incremental model-based reinforcement learning, where you are incrementally updating both your model as well as policy as you go. So in this problem settings, the standard MDP formulation takes two agents as entities. One agent is the agent, which is the policy agent, and it's trying to optimize the policy. And the second agent is the environment, where it's trying to model the environments. So this is a traditional MDP formulation. I'm going to manifest this into incremental model-based settings. So here, what is going to happen is our agent is tasked to simultaneously increment both the policy as well as the model parameters using interactions from the real world. And since the dynamics as well as the policy are making updates against each other, they are a non-stationary counterpart to each other. And this simultaneous development is quite tricky to stabilize and balance. Let's try to figure out why it is tricky and how we can stabilize this non-stationarity between these two learning objectives and develop new state-of-the-art model-based methods. So in incremental model-based reinforcement learning, there are two players that are simultaneously evolving using real-world interactions. The objective of the policy player on the left is to learn the policy parameters theta by maximizing the task reward J in the learned model M. And the objective of the model player is to learn model parameters phi by minimizing the prediction loss of the data that is collected by the policy in the model M. And this implies that both player needs to acquire different information to achieve their different objectives. And both objectives depends on parameters of the both player. That means the objective A depends on the parameter both A and B, and like vice versa for the otherwise. This indicates that model-based RL or incremental model-based RL is a general sum two-player game. And most existing algorithms have overlooked this competitive game nature of the model-based RL so far. At the equilibrium point of such a game, the policy is going to be near optimal, and the model will predict policy accurately. But getting to this equilibrium is somewhat tricky. So next, let me try to discuss some intuitions and how we can build algorithms on top that respect this interplay between these two conflicting objectives. Okay, so here is a metric, and I'm going to pitch different algorithms in this metric. Let's start. So I will argue that depending on the strategies of individual player, there are four broad ways of solving such games. On the primary diagonal are two meta algorithms with both players are going to simultaneously update their strategies while ignoring the existence of other player in the game. And both of these algorithms are suboptimal or unstable as they are unaware of the potential drifts in the objective due to the two-player nature of the problem. So here on the top is the model player, on the left is the policy player. So one class of algorithm, which is gradient descent ascent, is basically going to make small updates to both the player simultaneously and by ignoring the objective of the other. And on the bottom right, here is the best response where both model player and policy player are doing their best, but individually, they don't really pay attention to what other players do. And this results in conflicting objectives drifting away due to the non-stationarity between the two. Can we do better? And the answer is somewhat yes. That if we take the structure of the game into account, we can build on a formulation which is called Stackelberg games, which are generalization of minimax game and have been found to be incredibly effective in domains like GANs and meta learning. And the difference here are these are asymmetric games where instead of players ignoring the other players, they respect the other players and start taking turns. So for example, here, a model player, which I'm denoting by purple arrow, and the policy player by blue, is the model goes first, and then it will go for the policy will take turn, and the process will continue. So if we start respecting the notion of the game, there are different insights to solve these games more appropriately. So the key to solve Stackelberg games efficiently is to make players unequal. That means one player will play aggressively and in response to the conservative opponent, and represented here in the bold and thin arrows. The conservative player is going to induce its stability to the overall progress of the game, and it's called the leader of the game. So the choice of the leader naturally leads to the design of two families of algorithm here. The first, where the policy player is going to be the leader, and the second, where the model player is going to be the leader. And then they occupy the opposite diagonal in this spectrum I'm showing on the left. Okay, so I'm going to dig a little bit deeper into these individual formulations. Both of these formulations are very similar to each other, except they differ in two things. One, the order in which the players go. Here, the model is going first. Here, the policy is going first. And second, the strength of the individual players. So here, the model is the stronger one and policy is weaker. Here, policy is stronger and the model is weaker. And there are different ways one can make a player exist these aggressive or conservative strategies. And I'm going to make things more concrete by discussing two examples of algorithm, one of each algorithmic family. But note that these are two examples. One can instantiate a strong update or a weak update in any form that they want to. So I'm going to start with a PAL formulation, but let me wait really quickly and see if anyone has a quick question I can answer. All right, moving on. So here is a hand-arm system that I designed during my PhD to study the role of biological muscles and tendons in manipulation. And on the left is a real-time video of this hand going through its digit in merely 2.5 seconds. And hopefully I'm able to convince you that this is a very capable system, but actuated using 40 pneumatic muscles, which you see on these blue tubes. And they are notoriously difficult to control because these are third-order systems. So what we are going to do here is we are going to learn manipulation behavior on this system. So what we will do is we are going to emulate this framework called model predictive control, which I'm hoping that most of us should be familiar with. But we are going to use learned dynamics in MPC settings. And the dynamics will be presented using time-varying locally linear models and parameterized directly using the raw sensor data. The policy of this MPC algorithm, of this agent will be an MPC policy, which is going to be a linear feedback controller that outputs raw pneumatic voltages as desired controls. So note, there is no calibration or state estimation happening. We are directly operating at voltages coming in from these sensors and voltages going out to the valves. And we will learn behavior using PAL formulation, where the model player takes the first aggressive step, improving the model, and then the policy follows with a conservative step. So the algorithm starts by randomly initializing our policy as well as the model. At every iterate k, we first run the policy pi in the real world to gather a batch of trajectories tap. We're then going to fit the dynamics model m hat to this batch of trajectories using linear regression with Gaussian mixture of model priors. And this is our aggressive model step, where we are aggressively fitting the model to the current data. So you can think of this optimization going to the finish line. And using the fitted dynamics model, we were going to update the policy, maximizing the task reward. And this is going to be the conservative step, where what we are going to do is bound the policy update using the scale divergence between the old and the new trajectory distribution induced by the policy. And since we are learning a narrow model distribution, this bounded step prevents the algorithm from making sudden jumps and going out of the distribution. So this is how this leader, that is the conservative policy player, is inducing stability in the game to stabilize the overall algorithm by preventing us to move away from what we already know, and the model is making an aggressive step where it's overfitting to whatever it has seen so far. And in practice, this leads to a very extremely efficient method that works really well in the real world, even on high-dimensional contact-rate settings. Here we see its application to the task of rotating the object along the vertical axis. Note that there is no wrist and only fingers are responsible for maneuvering the object, which makes this task a little bit more challenging. We observed that different anchoring strategies from the thumb coming, and then a little bit of a nudge towards the end, again from the thumb and then the little finger to gain a little bit more task advantage. And it takes about 5 minutes of data to learn behaviors like this. And we have many more behaviors we have acquired. So here we are going to do is we learned the narrow model. Is it robust? Is the question. So what we are going to do is we are going to initialize the object in a bunch of random different positional as well as orientation error. And this is signified by noise in the initial state. And what we see is as the noise increases from 5 to 20%, the trajectories start deviating away from the nominal, but they are still able to reach the goal state and not catastrophically failing. So yeah, they are linear model, local model, but they are fairly robust for the tasks that you have learned so far. So while generating policies that are robust and efficiently getting to them could be one way of solving a task, but they exhibit limited generalization and adaptation to a slightly different task that you want to do. And this is because of the narrow support that you have learned in the model, this white band. As long as you can stay within the white band, you will be fine. So while efficiency is desirable, for next algorithm, I'm going to focus on a new algorithm for which generalization and adaptation is instead desirable property. And we will use this model as leader as a surrogate to explain this optimization process. So in this case, instead of building a narrow model that is efficient in solving a particular task, what we are interested in learning models that have wider support. And this is going to help with better generalization in case we change the task objective to something different than you have trained from, and as well as better adaptation in case there is a completely new task with a completely new goal manifold. So unlike previous example, where this time-varying linear model were sufficient, here we will need more expressive representation to capture the wider support of the dynamics. So what we are going to do is we are going to use a mixture of bootstrap ensembles of neural network to learn the dynamics model here instead. And an additional benefit of using the bootstrap ensemble is going to be that we can use the ensemble entropies as a measure of uncertainty during the planning process. So let me instantiate this algorithm and then we can pause a little bit for a discussion. So here is a quick recap of the MAL. The policy goes first and makes an aggressive update using the existing model. And then the model makes a conservative update using the policy data. So this algorithm, which I'm going to call PDDM, starts by randomly initializing the model as well as the policy parameters, which are phi and theta. Then we construct the policy pi using the current dynamics model. And note, this is our aggressive policy step, as the policy is updated aggressively under MPC setting. So we are overfitting to the best policy we can recover given the model so far. Next, the resulting policy is going to be executed in the real world to gather new trajectories. And in addition to practicing the task, few trials will also be directed to capture data around the uncertain region of the model, which is how we use the entropy of the model ensemble. That we use the entropy and we direct our exploration a little bit towards the entropy to improve the model in the areas which it's not good at. And finally, we will update the dynamics model with the collected data. And note that this final step is the conservative model update step, as we will only take few gradient steps over the entire data sets to ensure that the model does not change abruptly here. And this is how the leader, which is the conservative model player, is going to stabilize the overall game by inducing its own stability to the overall process. Any quick questions so far before I go into results of this algorithm? All right, let's look at the results. So this PDDM algorithm, which is based on the MAL formulation I just discussed, can solve a wide collection of contact-rich manipulation tasks. While PAL was able to do it in 5 to 10 minutes, here we are learning wider model support, and we tend to take a little bit longer. So here we are taking roughly half an hour, somewhere to all the way to 2 hours, depending on the complexity of the tasks. MAL is slightly less efficient than PAL, but still outperforms all other methods that we have tried, including on-policy, off-policy, and model-based methods. So here you can see some low-cost hardware on the left, rotating a valve. We have also flexible object, so there's a rope pulling using flexible objects, some die rotation in the hand, and some writing up, and then the bounding ball, which is not manipulation, not a single object, but 2 objects simultaneously, which makes the problem really, really hard. So let's dive deep into some of these results. So the first, let's look into bounding ball, which is an ancient Chinese relaxation technique where we are trying to rotate 2 spheres over a palm. And while manipulating a single object can be challenging, sharing the workspace with another free object makes this task extremely difficult. And model-based methods, while they have been found to be effective in smooth areas where there are not a lot of contact switches, this is an incredibly hard problem for model-based RL because we have to capture the intermittent dynamics of the resulting contacts happening in a very narrow manifold. And the representation power is going to be incredibly immense, as well as the exploration challenges are incredibly immense here, because we just end up dropping the ball if there is no coherent strategy. And while most state-of-the-art learning methods struggle in these cases, PDTM is able to convincingly solve the task merely in 2 hours, which you can also see how steep the extent to the success is here. And note that this is without needing any prior information about the task or the demonstration. We do not bootstrap it using any prior policy or prior data or model. And this result, I will say, is quite significant when you contrast with the fact that model-free policy gradient techniques take over 20 hours to solve OpenAI gym tasks like swimmer, cheetah, etc. So next, we are going to test the generalization capability of PDTM on the task of handwriting. Here we are training on random trajectories. So you don't have any legitimacy in those behaviors. You are just trying to train for random scratches on a piece of paper. And on the inset below, we are testing on finally writing numbers on it. So you can see from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's test case, which was not included in the training case. And I'm showing one of the zoomed out version for number 3 over here. So as we can see that in the task of handwriting, we are able to get quite generalizable behaviors. In terms of training, we see similar performance. While most of other methods not even succeed after a really, really long amount of time, PDTM shoots really aggressively towards success, and it's able to deliver generalizable policies that can write most of the numbers. Okay, so I think generalization is somewhat there as well. What about adaptation? So remember, adaptation is we haven't trained for these goals, and we are hoping that the model support is wide enough so that new goal distribution can be captured 0 shot. We are not trying to do any more training. So here what we take is we take the model that was trained on anti-clock rotation with 2 spheres, and we are going to test on clockwise rotation. So the clockwise rotation was never tried, and you can see the clockwise rotation here is quite meaningful. The second, what we are going to do is we are going to even strip the space into half, the object space. So we trained a model on 2 balls. Now we have dropped 1 ball and asked only to use the acquired model to position the ball to this red sphere. And we say, see, this is actually possible as well. So there is some adaptation capabilities in this model happening, and this is due to the model formulation and the wider model support that we have learned so far. So now, are these things real world ready? So to investigate, what we did is we let PDTM algorithm run in the real world, fully autonomously acquire this. So what you just saw was a reset mechanism on which if we lose the ball accidentally, there is another robot that just comes and brings up the spheres up on the palm again. And here, the algorithm basically starts by random motor babbling. And you'll see you quickly lose the ball. In about half an hour or so, we start seeing behaviors that understands that, okay, losing the ball is not helpful. At least I need to keep the ball in the palm. In an hour and a half or so, we'll start seeing some rotations happening, half rotations, sometimes 180 rotations. And in about 2 hours of real world experience, we see consistent rotations that are happening throughout the behaviors. And note the input to the space is an RGB image, and the output are desired joint angles that goes in these fingers. Okay, so now I have pitched to you that incremental model-based RL is a 2-player game, and based on Stackelberg formulations, we can look into 2 different class of algorithms that can be quite interesting, and they are efficient as well. So first, we look at PAL formulation. Here, the model player aggressively improves the model at the inner level, and then the policy player, which is the conservative player, takes the conservative step at the outer level. Conversely, under the MAL settings, policy first takes an aggressive step using the existing model at the inner level. and followed by the conservative step, model update step, using the data from the optimized policy at the outer level. And then we looked at few state-of-the-art algorithm using each one of these algorithmic paradigms. So next, I think what I'm going to argue is there are differences between these two. And I'm going to highlight what are the nuanced difference between these two and why one might prefer one versus the other. But before I go there, let's see if there are any quick questions I can take.
Vikash, how sensitive is this algorithm in terms? So you say you take only a few epochs or only a few gradient steps when you're updating the model. So how sensitive is it to this parameter?
It's not as sensitive. I don't think we ever, did a hyperparameter search on that. We just kind of picked like one or two gradient step and ran with it. But I would envision that if you make it aggressive, efficiency will rise, but it will get more unstable. So that's the playoff that I will see over there. So the idea here was just to make things aggressive and conservative. And so since it was the hardware settings, we made aggressive one really aggressive and the conservative one really conservative. But I can assume that you can make the conservative a little bit aggressive by making like 2 or 3 steps instead of just one.
Okay.
All right.
Vikash,
yes.
I wonder, you could have tried a narrow version of the bouting balls or a more global version of the hand twirling. Did you try either of them? Did you compare the opposite methods across your examples here?
Yeah, I will show you next slide. That's exactly the next slide. So it's basically the diagonal elements where you're ignoring. So if you make both of them like equally aggressive, equally conservative, they start ignoring each other's presence. So I'll show that result next. Okay, so let's move on. So now let's zoom out a little bit and ask the question if the game theoretic underpinning of this incremental model-based RL was indeed helpful. So what we did here is on the task of pen manipulation, we are going to compare both PAL and MAL against other algorithms that do not take the game theoretic aspects of model-based RL into account. So again, these are the diagonal and the algorithms that we have developed are off diagonal. So what we will see is these diagonal elements, which are the gradient descent strategies as well as the best response strategies, like make really slow progress and they are quite unstable. But we find that the PAL in blue and MAL in green are significantly outperforming the non-game theoretic counterparts, which highlights the benefit of treating this model-based RL as a game. So even like one would assume if you make both of them incredibly aggressive, then we should have better efficiency. But in two-player game literature, it's very well known that best response strategy ends up creating a lot of jitter, and they end up like drifting away from the support of the other player. So that hopefully answers the previous question.
Well, Vikash, sorry, and I'm sorry my video is not on. I'm kind of, but so you could have done the bouting balls with the local linear models, yeah? Did you ever try it? I mean, you sort of said you couldn't, but I don't understand maybe why you couldn't actually do the, the local approximation of that.
Right. So I think what we tried it in simulation, so I don't have it in the real world. So we tried it, and basically what happens is the support that you are going to build in the local model case, soon the balls are going to go out of that support. So they basically do not develop the model and the policy coherently together. But I think if we tune it hard enough, it should be possible, but it doesn't lead to a stable algorithm. So we tried like a lot of these things in simulation.
And then the other side, if you're spinning the whatever you're spinning there, could you have done that more globally with the neural net model?
Yes, I will. I should be able to do it, but I think it will be slower than the PAL formulation because now we are capturing the model a little bit more aggressively, and the policy takes the backseat here. So I think it's possible it will be slower than what I showed you. And it's kind of evident in the results here as well, that here we take like roughly about an hour worth of time to solve it, whereas the spinning one we were able to solve in 5 minutes.
Awesome, thank you.
Yeah. Okay, so next, let's see if the Stackelberg formulation of stabilizing the game was indeed helpful. And how do we compare against other state-of-the-art model-based algorithms that have been designed using various different strategies? And what we find here is the stability that is induced by the Stackelberg formulation, PAL and MAL, delivers the new state-of-the-art methods on standard continuous control benchmarks. And here we have PET, Steve, SLBO, SSC, which is an off-policy method as well. So you can see that we really accelerate aggressively. And most of these methods will eventually catch up, but I'm just showing the initial part of the training over here. And finally, I'm going to ask the question, what is the broader significance of these two Stackelberg formulation? Both seem to be working well. The interesting bit here is that these two formulations have very complementary strength. So when the dynamics is non-stationary, such as think of like a sudden gush of the wind that you cannot predict, the PAL has better adaptation. Why? Because it's aggressively overwriting the old inconsistent model. So in this graph, we will see that PAL recovers faster after the change in the dynamics, which is marked by this arrow. Now, when the goals are non-stationary, think of like if you're driving and suddenly some pedestrian occurs. So the goals are completely obliterated and you're solving towards a non-goals, towards a different goal. So in this case, the goals are non-stationary. And in this setting, the MAL will adapt better as it aggressively overwriting the old inconsistent policy towards the previous goal. And here is the same graph with the star representing the change in the goal. So in summary, what I'm claiming here is the Stackelberg formulation are providing guidelines and recipes for building algorithms that are tailored toward handling different types of non-stationarity. So yeah, they are giving better algorithm, but they have two different flavors when you think of non-stationarity in your system. And the overall game theoretic framework for model-based reinforcement learning connects the field of theoretically rigorous game theory with the field of reinforcement learning. And I believe this connection will have a very significant effect as we develop and mature our algorithms further. So the sample complexity of our algorithm is significantly better than both state-of-the-art off-policy as well as on-policy algorithm, which is clear. But like, come on, like no benefit comes from nothing, right? So where do we lose? We really lost in compute required, because we are building these models. So some amount of compute goes in building this model. And so we are not as compute efficient as all policy method. But I think the trade-off, if we have to pick between efficiency from the real world samples to compute, I think it strikes the correct balance that offloading some of the sample efficiencies towards compute, which is easily scalable. Well, to summarize, I think we identify a model-based RL algorithms as more incremental model-based algorithm at the core, and it is a two-player game. We designed new state-of-the-art algorithms based on Stackelberg formulation, which also provides us with recipes to handle different kinds of non-stationarities. And now let me highlight a few key takeaways from this part of the talk. The techniques I'm discussed today are efficient. They train behaviors directly in the real world, and they are broadly applicable. While I centered most of the results here around manipulation, we have actually the same algorithms working on locomotion domains as well. Okay, so let me pause here and see if there are quick questions around this part of the talk.
Maybe I'll ask one more. So why do you call it a Stackelberg game instead of just a two-time constant thing? Would you call actor critic similarly a Stackelberg game? You know, when you know you have to train your critic more slowly than your actor, would you consider that also a Stackelberg observation, or would you not think there's more game here?
In some lens, I can call that Stackelberg formulation as well. So like note that I'm not designing any Stackelberg formulation, which is new. I'm just borrowing these conventions that are known conventions in the game theory literature on solving these games. So I would say that, yes, actor critic can be also rethought. A Stackelberg formulation, maybe some small, change in perspective might be required. But yeah, so the change in perspective here that was required is basically to make the players go in succession, and in incremental model-based RL, if we dig down in the theory, I think we were able to make that stepwise, that one player goes first, the second goes after. Yeah. Okay, so I think I have two more sections left, so I'm going to just run through these ones, not cover as as much in detail, and I'll try to see if I can cover some of this and then wait for questions at the end. So I'm going to argue that while we got some practical techniques that are working, are they really real world ready? And this is where the applicability of why we are not creating impact might come into question. So if you have that hat on, I think you'll enjoy this section a little bit more. So while I showed you these two incredible results, here is what the real world setup for these results look like. They are explicit reset mechanisms or helping agents that are helping these robots acquire these skills. And arguably, more impressive work is being done by these agents, and they take most of the training time that is required. And this is not the case only for my system. I'm going to argue that that's the case for most of the systems that we observe out there. What is happening is we have careful instrumentations or interventions by humans, or explicit reset mechanisms that are bottlenecking what we can do right now in terms of operating in the wild. So the question becomes, can we remove some of these constraints so we can achieve true impact of scalable learning? So the argument over here that the algorithm should be able to set up their own problem. Explicitly needing reset, which needs another agent, is where the bottleneck is. So once you complete one episode and you're successful, you should know what to do next. And the question here is, if we change the paradigm from the single task RL to multitask RL, does this somehow remove this problem? And my argument is going to be yes, because we seldom need our agents to do one thing at a time. So if we have a robot in the kitchen, we want it to open cabinets, pick up kettle, move the kettle from one place to other, etc. So can this reset-free problem will be easier with multiple tasks? And the insight over here is that yes, when you are solving multiple tasks, each one of them can start becoming a reset mechanism for the other. So if you are picking up a kettle and you dropped it, lifting a kettle or lifting an object and then putting it back on the countertop is going to be helpful in those dimensions. So more concretely, what I am going to show you is I'm going to give a successful example, which is on the picture on the right. So in-hand manipulation, where you have to pick up an object, put it on the palm, and then we are going to see if we can train these things completely reset-free. Okay, so what happens if we train without resets? So yes, you will start by exploring, and soon what you will see is, you drop the object. And after that, no matter what you try, you're never going to pick up the object. So more concretely, what our algorithmic instantiation will look like is we're going to simultaneously learn a collection of different tasks in this setting. Some involves recentering in the middle, other involves picking up, other involves rotating and reorienting, etc. And each one of these are going to some way reset the other mechanisms. So no matter which state we find ourselves in, we are going to attempt whatever is possible from there. And when we succeed, we end up in the initial state of some other problem. So let's just say we are trying to lift. So in this case, we fail, and then in that case, we are going to try recentering. If we succeed in recentering, we're going to lift the object again. Once we lift up, then we can try flipping up from there. We can drop it again and try lifting again. We can try in-hand reorientation if the flip up is successful. And then eventually, if you drop again, you can start recentering, etc. So what the whole process is going to look like is somewhat like this, that in some time we are going to drop the object, and then we are going to spend a lot of time trying to get a hold of the object, understand how to orient it in our favor. So in this particular case, we are trying to recenter it in the middle and see in about 20 hours or so, we see that the hand has roughly learned good recentering strategies. It has also tried other tasks. When the recentering succeeds, then you will see that recentering is acting as a reset for lifting up. And then lifting up behavior starts emerging while it's using the recentering as its reset policies. And after a while, we will see that both recentering and lift are providing resets for the flipping up behavior. So in 40 hours or so, we have flipping up behaviors coming. Right. And in some time, we will see that now in-hand manipulation starts. So more finger level behaviors are starting to emerge, which are trying to position the object where it actually needs to be positioned. So in about 64 hours or so, here's the final behavior, lifting up, and then final integrate behaviors of the fingers to reposition the object properly. So we have another system like this where we tried inserting a pipe. And the same process happened over here, that you try to get hold of the spigot, and then you try to lift up in a lot of time as you progress in the training. In about 20-24 hours, you start lifting up, and then you align the hose properly, and then you try insertion. Maybe you're not happy, and then you're going to retry and going to insert this object again. Okay, so this is these behaviors are acquired completely reset free. We have some other behaviors in the simulation, inserting a light bulb here, maybe using a basketball dunking task again over here, etc. So I'm going to skip the takeaways and last part of the talk in the interest of time, and then do like one last slide over here, that most of these progresses are progresses over a long period of time in terms of how we took our algorithms to the hardware. And initially we started with setups that are more elaborate. I showed some hand setups that cost over $500,000. And soon I realized these are not scalable. So here is an attempt to provide scalability to these systems. There are some robot platforms. These platforms are fairly cheap, around $3,000 to $4,000. They're low cost, can be deployed in home, outside settings fairly easily. And they have collected over 35,000 hours of real world experience at that time. That's like roughly 3.5 years worth of data for you. And I also showed some dexterous hand results, which has over 2,000 hours of real world training on them. So these robust systems are what we need, and cheap systems to scale our algorithms in the real world. And with that, I'm going to thank my collaborators, and here are some papers that I covered in the talk. All right, thank you, everyone. I'll take some questions.
Thanks, Vikash.
Yeah.
So one question about the reset free work that you were presenting. So did you have explicit classifiers which said now try recentering and now try picking this up?
Yeah, so we have just partition of the space. So there are just like, if the height is below this, then this task can be tried. So right now that part is hand specified for the experiment that I showed you today. But what we have done next, so like this graph, like on the top, basically when can you transition from which phase to which phase is hand specified at the moment. But what we have now is we have taken some offline data from some successful runs, and then we have automatic mechanisms of just classifying these tasks from that offline data. And it turns out that's not at all hard. If you just like have some offline data, this can be automatically acquired. But then the assumption is you have some legitimate offline data to do this.
Okay. And how are you measuring the rewards over here? Is there some sensor in the white thing, or is it all camera?
So here, like there are some markers attached to that. So this is a state-based result. So we have some other results which are not reset free, but we have acquired these similar kind of behaviors based on vision. So I think we are trying to connect the two dots right now. But this is a state-based result. We have explicit tracking of the object.
Okay.
I have a question.
Yeah.
Very nice talk. I really like that was fantastic. I have a sort of like perpendicular question is, what's your view on like a tactile sensing, and what is actually the technical difficulties that prevents people from actually like using them like in these manipulation tasks?
Right. So I think tactile sensing has very complementary strength when it comes to vision or like joint angle sensors. like let's contrast with vision. Vision is really great at giving you global information, spatial relationship between these things. And the moment you get close to the object, you start losing that context because it occludes the object. And that's exactly when the tactile sensors become relevant. And then they give you the information of like the local details that is needed for fine manipulation. So I think they have complementary strength, while you're correct that we have not been as successful in exploiting the tactile modality as much. I believe a deeper exercise is needed into what matters in tactile sensation. What we have done right now is we just dump the tactile data and assume that that's enough. I'm going to argue that the tactile information is much more nuanced. What really matters are not the signal itself, but some temporal component or temporal signature of the signals, maybe some Fourier domains, etc. So I think what we need is some way to capture the temporal aspect of tactile. And once we figure out what that aspect is, they will start becoming much more useful. But so yeah, I'm on board that I think that they should play a more aggressive role. I think we need further development in order to get there.
I see. So you're saying that we're overfit to basically the texture part, but we're like not, like we're kind of like not like looking at like slippages or like other things, stuff like that.
Yeah. So the dynamics of contacts, like in biology, are very well understood, that they fire on the onset and then they decay over time. So it's not a signal that we use like in real time. They have internal dynamics of their own, and maybe some of those things help us as humans to get these behaviors, and maybe we need some similar kind of investigation to see maybe how to make them better useful.
Yeah. I think even like a texture itself is actually like done by like a basic temporal structure, by like having your fingerprints, like grooves rubbing against the actual physical texture. So yeah, I agree with that. That's a good point. Yeah.
Yeah.
Thank you.
Vikash, in your MPC work, once you have a deep network model, you have a relatively weaker set of tools for planning, and your horizons were pretty short, I think, in that work. How constraining did you feel that to be? Are you pining for better planning algorithms with the deep models, or do you think it's good enough for the tasks you care about?
Two-phased answer is one phase when we are selecting the tasks, we're mindful that we shouldn't pick tasks which are explicitly need long-term reasoning. But once we had like a mental model, every task that we came up with, we're successful. So we didn't have to iterate too much on that, but we started with the objective that it shouldn't be too long horizon. So conscious choice, but not overfitting to these tasks. But the second point is, I think they are limiting in terms of solving long horizon problems. Our prediction gets noisier as we go longer in the horizon. And those are some of the problems that we are starting to look at, is how do we pose model-based RL in slightly different light, so that we can start to solve long horizon problems. I'm happy to discuss.
So those are two different things. I guess there's the model being able to predict in a long horizon, and there's the planner. Let's say the model was perfect in a long horizon. The planner is still tough. Which one do you think is a more painful limitation?
I would say the model. Because I'll be happy to go into detail later, but the PAL and the MAL formulation internally are not using a trajectory optimizer. They have a full-blown policy planning going on, so we can potentially push that up as far as like at least model-free planners, model-free policy updates can take you. But in some recent work, we are actually trying to remove the time discretization of MDP and see if we can actually build arbitrary time step and MDPs, so that where the resolution of the behaviors doesn't matter, can we take bigger MDP steps? So still we are going to be planning in 100 horizon or something, let's say, but each one of individual step will be variable time steps. So eventually we'll be able to like ramp up the planning horizon by maybe 10x. But yeah, long horizon problem, which is the order of magnitudes of minutes or hours, I think that will need a complete rehaul, maybe hierarchical reasoning or like some high level concepts that directs the low level. And the low level is short horizon, where the high level is doing sequential planning or decision making on the coarse grained. And then the lower level does the short horizon plans. Those kind of paradigms might be helpful there.
So let's thank Vikash for the talk once again.